Okay, all right. Well, sorry for this complications. Didn't happen yesterday, so I don't understand. So the title of my talk is on the existence of the fundamental transfer matrix in quantum potential scattering, propagating wave approximation, and exactness of the Bode approximation. So this is a joint work with my former student, Farhang Loran, who is a professor at Istanbul University of Technology in Iran. The outline of the talk, I'll start with very simple introduction to potential scattering in quantum mechanics in 1 and 2 dimensions. I talk about its dynamical formulation. Then I will explain what we mean by propagating wave approximation and non-local potentials which appear in the construction of this approximation. I will talk about the existence of the transfer matrix for this propagating wave approximations and its exactness. And I'll continue with showing you the first examples of potentials for which the nth order Born approximation is exact, and conclude with some final remarks. So in 1 dimension, by potential scattering, we mean the scattering theory defined by the time-independent Schrödinger equation, where this potential V is a short-range potential, which means that at asymptotically it decays faster than 1 over x. This allows to obtain the following asymptotic expressions for the solutions of the time-independent Schrödinger equation. Essentially, it means that at infinities, it behaves like a plane wave. These A's and B's are coefficients of right-going and left-going waves at x minus infinity and plus infinity. So you have this picture. And there is a 2x2 matrix which connects these coefficients. The coefficients at plus infinity are related to coefficients at minus infinity by this 2x2 matrix. This is called the transfer matrix. And if you assume that this transfer matrix does not depend on this A minus and B minus, that means it defines the linear operator, then it is unique. So among the solutions, there are so-called scattering solutions. This is a left incident scattering solution, which means that at minus infinity, there is this incident plane wave, which goes to the right. Parts of it gets reflected, and parts of it gets transmitted. And these coefficients are called reflection and transmission amplitudes of the wave. You can also have a wave sent from the right, and again, parts of it gets reflected and parts of it gets transmitted, and these are called reflection and transmission from right. So if you look at these scattering solutions and apply the formula for the transfer matrix, you can identify these A's and B's for these solutions. You can show that these reflection and transmission amplitudes are given as ratios of the entries of this transfer matrix. The left and right transmission amplitudes coincide, and this is called reciprocity. And it's given by 1 over M22 entry, and the others are also ratios. So if you know the transfer matrix, you know the reflection and transmission amplitudes, and that means you have solved the scattering problem. Now, what makes transfer matrix important is its composition property. So suppose you have a short-range potential V, which is dissected into 2 pieces, V1 and V2. The support of V1 is to the left of the support of V2, as I have tried to demonstrate in this graphs. And if V is a short-range potential, so are V1 and V2. So you can assign transfer matrices for V, V1, and V2, and it turns out that the transfer matrix for the sum is the product of the transfer matrices for each of the pieces of V, V1 and V2. And there's an ordering involved. If the support of V1 is to the left of the support of V2, then the transfer matrix of of V2 comes to the left of transfer matrix of V1. Now, many years ago, in 2013, it occurred to me that this composition property is identical to the way evolution operators in quantum mechanics are composed. That is, if you have a quantum system and you have a state of your system at time t0, if you want to evolve it to time t2, you can also evolve it to an intermediate time t1 and evolve the state vector from t1, t2. And the total evolution operator will be just the product of U1 and U2, which has the same structure as the compositive property of transfer matrices. Now, let me remind you what these evolution operators are. So evolution operator is a linear operator which takes an initial state vector and maps it to the state vector at t. Obviously, it depends on an initial value of time t0. If you evaluate u at t0 for consistency, you know that this should be identity. And if psi of t solves the time-dependent Schrodinger equation, then this u satisfies this operator Schrodinger equation, and everything now happens in some separable Hilbert space. And these are operators acting in this Hilbert space. Now, you can write this differential equation as an integral equation, and then try to substitute the right-hand side for u to the u appearing in the right-hand side, and iterate this procedure. You get a series, a formal series expression for this evolution operator. This is called the Dyson series. And as you see, the variables of time which appear in this product of the Hamiltonians are decreasing. So Tn is going to be bigger than Tn minus 1 and so on. So this is a kind of time-ordered products of these Hamiltonians. This H is called the Hamiltonian operator. And the shorthand notation for this Dyson series is to use this expression, which is called the time-ordered exponential. This looks like exponential. It can be made look like exponential by producing this thing. But throughout this talk, this symbol is just this symbol, this right-hand side of this means just this Dyson series expansion. Okay. Now, I could show in 2013, the late 2013, that actually what I expected is true. The transfer matrix for the potential happens to be given by a time the evolution operator for some quantum system. It's a two-level quantum system. The Hamiltonian is a matrix Hamiltonian, and it has a universal structure because the potential appears as a coefficient. And here you see, in place of time, there appears this x, which is the coordinate of space. So this x plays the role of time. And since this is a 2x2 matrix, it acts in a two-dimensional complex Hilbert space of 2x1 matrices or column vectors with two entries. Now, because this depends explicitly on this effective time variable, the evolution operator is given by some time-ordered exponential, and therefore you are led to this formula for the transfer matrix. Transfer matrix can be expanded in a Dyson series expansion involving this particular matrix Hamiltonian. Now, this matrix Hamiltonian can also be written in this form here, where this K is just this nilpotent matrix. Sigma 3 is the third diagonal Pauli matrix. And it's very easy to show and to see that this Hamiltonian is not a Hermitian matrix. So it doesn't define a Hermitian Hamiltonian operator, which is usually the case in quantum mechanics. It's even worse. It's not even diagonalizable. Its square is 0 because K is nilpotent, and the 0 is only eigenvalue. So this is the worst possible thing that you can imagine, and it's disregarded as not allowed in ordinary quantum mechanics. But this is quantum mechanics, it's scattering theory, and this potential can be real or complex. For real case, you have a unitary evolution, but still scattering is defined by this non-Hermitian and non-diagonalizable Hamiltonian. Now let me try to generalize this to 2 dimensions. In 2 dimensions, again, the scattering is defined by the Schrödinger equation. And if I want it to be short range, it should go to 0 faster than 1 over r to the 3 over 2. If this happens, then there are these so-called scattering solutions, which asymptotically satisfy this expression here. Again, the first term represents an incident wave, incident plane wave. K is the incident wave vector for that wave. And that the second term is what is called a scattered wave. Everything is fixed except this f of theta, which is called the scattering amplitude. And the aim of solving the scattering problem is to determine this f of theta for given potential V. Now, the quickest way of dealing with the scattering, potential scattering, is to use this Lippmann-Schwinger equation, which you can follow using the Schrödinger equation, write it like this, and then standard method by Green's function, you get this kind of integral equation, which is equivalent to this. This is G plus, it stands for the Green's function, which corresponds to outgoing waves. These are the Green's functions for the Helmholtz equation with outgoing boundary condition. In 2 dimensions, it is given by Hankel function of the first kind, h and order 0, h10. And you can use the asymptotic expression for the Hankel function to find the asymptotic form of this solution, and you recover this formula that I gave you earlier, and it also this asymptotic form of the Hankel function gives you a formula for f of theta, which I have listed here. Again, this is not very useful because this formula, the integral, involves psi of x, which is still not known. So you have to solve the Lippmann-Schwinger equation and substitute here to get the scattering amplitude. Now, if you write the Lippmann-Schwinger equation in an operator form, it takes this simple form. This psi 0 is just the incident plane wave. G plus the operator is the resolvent corresponding to this Green's function of the Schrödinger operator. I define it using this formula. And V hat is the operator of multiplication by V of x. This is the ordinary X representation of quantum mechanics. Now, if you take the second, this operator form of the Schrödinger equation and use it to find this psi on this right-hand side, and you iterate this, you get a series, the formal series solution for the Lippmann-Schwinger equation. Now remember, we had this formula for f of theta, and you can substitute the series here, interchange the integration with series sign, and that leads to a series expression for the scattering amplitude, which is known as the Born series, discovered by Born in 1926. And you can also find the explicit form of the terms in this series. Just substituting this formula here, it gives you this FLs, L running from 1 to infinity. And when you calculate FL on the right-hand side, there are precisely L copies of V. So if V is a weak potential and you have a coupling constant, so this will be of order L in coupling constant. So essentially, this is a perturbation series. And if you truncate that series after n terms, you obtain an approximation, which is known as the nth order Born approximation. Okay. So next, consider regions where the potential vanishes. Then the Schrödinger equation becomes Helmholtz equation. And there are 2 types of solutions of this equation: the oscillating solutions or plane wave solutions, which have this form, where this P runs from minus K to K. It's a real parameter. And this square root is real. So this is an oscillating wave. Or you can have exponentially growing or exponentially decaying solutions, where this P is outside this range minus K and K, and you have this formula, and this is the exponentially growing and decaying parts. In general, the general solution is linear combination of this kind of solutions, where this omega of P is defined to be just the principal value of K squared minus P squared. So it is K squared minus P squared when absolute value of K is less than K, otherwise I times that. Now, imagine this special case where the potential vanishes outside this strip. So for X not inside in the closed interval A1, A minus A plus, suppose the potential vanishes. So we have a picture like this. Then, and outside of that strip, the potential vanishes, and the solution can be written as a linear combinations of oscillating solutions. This is to the left of the interaction region. This is to the right. And also evanescent solutions. These are exponentially growing and decaying ones. So because for X less than A minus, you can approach minus infinity, and for X bigger than A plus, you can approach plus infinity, you shouldn't allow for exponentially growing solutions if you're interested in bounded solutions. So only you get e to the plus absolute value for X less than A minus, and e to the minus absolute value of omega X for X bigger than A plus. These are the coefficients of this superposition of these weights, A's and B's. A's and B's are functions of P, and P runs from minus K to K, and I will assume that they are 0 outside the interval minus K to K, and C's make a difference when P is bigger than K or less than minus K. So I assume that C plus minus vanish inside the interval minus KK to make these functions well-defined. And this omega P is what I described before. So this is essentially using Fourier transform to write the general solution in the superpositions of these oscillating and evanescent waves. Now, to make life easier, I introduce this F, which means set of complex valued functions. And by functions, I allow also distributions, temporal distributions. So what I need is the existence of Fourier transform. And Fk are elements of F which have support inside minus K and K. These are functions of P. So by this definition, this A's and B's, which vanish outside minus K and K, belong to this Fk. Now, if you look at the asymptotic form of the solutions, so the evanescent wave will decay away, and only the oscillating waves survive when X goes to plus or minus infinity. Now, so you have very similar situation to the one-dimensional case, and I will use my knowledge of one dimension to define something like a transfer matrix using the same formula. The only difference is that now these A's and B's are not numbers. They are functions of P, and this M is actually a linear operator, which takes A minus B minus to A plus B plus. So because these A's and B's live in this Fk, this M is a linear operator from Fk squared to Fk squared. Next, let's compare the asymptotic expression I found using this setup and the asymptotic expression using the Lippmann-Schwinger equation, that they must agree. And this says that this f of theta should be related to A's and B's somehow. Now consider right incident wave. What does that mean? It means that the source of the incident wave lies on the plane x equals to plus infinity. I try to show it here. So there's an incident wave with angle theta 0, incident angle theta 0, coming toward this strip where the interaction happens. Then nothing comes from the left, so there is not going to be no right-going wave at x equals to minus infinity. That means a minus should be 0. And b plus, which is precisely the incident wave, you have to choose this delta function here to make the asymptotic formula, the first line with x minus infinity, to generate this incident wave, plane wave, e to the ikx over 2 pi. So a minus and a plus are fixed. And then substituting in the second and comparing, you find this formula for f of theta. So I need a plus and b minus. A minus and b plus are properties of the incident wave. A plus and b minus should be obtained from the potential. Well, let's write these formulas in terms of functional inequality. So a minus is 0 function, b plus is a product of a constant times the delta function. This is Dirac delta function. And then you impose this condition, which is just a definition of the transfer matrix. You find these formulas for b minus and a plus. So the first line is an equation for b minus. The second one gives a plus in terms of b minus. So you substitute back in your formula for f of theta, you see that this gives you a method for solving the scattering problem. That means you have to find the solution for this equation, and we will see that this is actually an integral equation. And then you find b minus, put in the second equation, get a plus, and then using this formula, you get f of theta. Okay, that was when I send a wave from the right-hand side. You can also send a wave from the left-hand side. Repeating the same analysis, you can find that the formula for the transfer, for the scattering amplitude is given in terms of a plus and b minus. This a plus and b minus are obtained by solving an integral equation here. And then this is just a plus as a function of b minus. So in each case, you obtain an integral equation. And I will show why these are integral equations. Okay. Some notation. I will use a tilde for partial Fourier transform with respect to y. So it's a Fourier transform with respect to y of functions of x and y. And f stands for that partial Fourier transform. And f inverse is its inverse. Also, I need this projection operator, which maps functions to those which have support between minus k and k. This is capital pi k. Now, it turns out that this operator m hat, which I introduced, admits also a Dyson series expansion, very similar to the one-dimensional case. The only difference is that I need this projection operators to the left and right of the Dyson series expansion. This h of x is, again, a linear operator, which has this form. Here, this omega hat is just multiplication by omega p. Omega p was the principal value of k squared minus p squared. Sigma 3 is the Pauli matrix. K is the same nilpotent matrix we saw before. And y hat is actually just differentiation. So this x y hat is a non-local operator. You can express it in this form in terms of its partial Fourier transform. So it's a convolution operator, really. So because this v is an integral operator, the h actually is an integral operator as well. And the Dyson series involves integral operators. You see that this m is going to be an integral operator. Okay. Now let's go back to our form of solutions outside the interaction region, where I could write the solution as superposition of oscillating and evanescent parts. Well, the oscillating part you can express in terms of this partial Fourier transform and inverse partial Fourier transform and this projection operator. So you have a shorthand formula for the oscillating part of the solution outside the interaction region. Now I will take this formula as a definition of oscillating part of the solution all over the x-axis. And the remainder of the solution, which is psi minus psi oscillating, I will call evanescent part of the solution. This defines the oscillating and evanescent part of the solutions throughout the whole plane. And the propagating wave approximation is the approximation in which I will neglect the evanescent part of the solution everywhere. And that's a huge, strong condition. Now, it turns out that propagating wave approximation is equivalent to replacing the potential which defines your scattering by a non-local potential, which has this form. So this non-local potential is given by the partial Fourier transform of the potential with respect to y and this convolution integral. Because k appears, k is a measure of energy, so this is energy dependent, and because there are integrals appearing, this is a non-local potential. So propagating wave approximation is equivalent to looking at the scattering problem defined by this non-local energy-dependent potential. Again, let me backtrack. The transfer matrix was a linear operator mapping f2k to f2k, where f2k are functions which vanish outside this interval minus k and k of p. We had this Dyson series expansion, which involved this Hamiltonian operator h. And now we look at what happens when we do propagating wave approximation. When v is replaced by this non-local potential, it corresponds to changing this operator, which has operator v, which is x, a function of x and y hat, by the projection of it from the left and right. So this equation. So if you replace this v by this pink vk, you are doing propagating wave approximation. And that corresponds because this projection operators commute with these exponentials, because it commutes with omega. You can also see that propagating approximation, wave approximation, means that rather than this h, you use its projected form. Similarly, you can look at what happens to the transfer matrix. If you change h to this projected form, you replace this h by this h sub k. But h sub k is already having this projection operators to both of its left and right. So you really do not need these two projection operators in definition of the transfer matrix. So you get away with writing down this as projection operators because these are already projected. So you have this Dyson series expansion for the transfer matrix when you apply propagating wave approximation. Okay. Now, again, the general form of a transfer matrix, if you write the first three terms, you see the first linear term in the first term after the identity already has projection operators about the Hamiltonian h, so you can replace it by hk. But the second one doesn't have a projection operator between two Hamiltonians. This shows that if you neglect the quadratic and higher order terms in this series, you are doing precisely this propagating wave approximation. Now, you can neglect the quadratic terms if the potential is, because two copies of h means product of two potentials. So for weak potentials where you can neglect the second and higher order terms in the Dyson series, the propagating wave approximation is a valid approximation. So this is a weak potential approximation. Now let's take this example. Suppose that the potential is the product of the delta function of x in one-dimensional delta function of x times a function of y. Then substituting this formula here, the formula for h simplifies. It's just proportional to this matrix K. And that means that its square is 0 because K squared is 0. And K commutes with these operators. And because of that, all the terms in the Dyson series vanish except the first two terms. But first two terms agrees with what the propagating wave approximation gives you. Therefore, for this class of potentials, this approximation is exact. Now, if you take this function g of y to be also a linear combination of delta functions, then you have actually a potential which is a sum of two-dimensional delta functions lying on the y-axis. Now, using our method, you can solve those integral equations I gave you and get the exact solution for this problem. Exact formula for the scattering amplitude is given by the inverse of this matrix AMN. This AMN are the entries of the matrix, which has this form. Now, this is a very old problem. People discovered this, that if you apply the Lippmann-Schwinger equation, you encounter infinities and you have to do renormalization, the regularization of infinities and coupling constant renormalization. It gives you the same formula that I derived here for one delta function. But I don't need any renormalization. For more than one delta functions, the formula I have differs from the one brute force renormalization, because here I have Bessel J. The renormalization procedure gives you Hankel J, Hankel function, H0, but that leads to a contradiction with itself. And this is called the coincidence limit problem. If you take two of the delta functions and look what happens if they approach and collide, then the Hankel function blows up and you get 0 for the scattering amplitude. Whereas in our case, when two of the delta functions coincide, you precisely get the same formula with one less delta function, which is what you would expect. This paper describes why this happens and how you get around it. With renormalization procedure, the problem is that the renormalized coupling constants can also depend on the position of the delta functions, but renormalization scheme usually does not tell you how this dependence happens. In our scheme, there is no renormalization. This is the ordinary Bayer coupling constants, and everything is fine. Okay. Now, what I described involved taking some limits, looking at some series, but these are operators. So all this material can be looked at as a formal constructions. There are mathematical questions that should be asked. For example, when we talk about this Hamiltonian, what is the function space this operator acts? What is the domain of this? Is it a densely defined operator or not? And does that generate really a dynamics? That is, does this Dyson series converge in some sense? And even it converges for finite x and x0, does this limits when x and x0 go to plus or minus infinity exist? These are operators, and one has to deal with the existence of limit of these operators. Now, what we could do was to answer these questions within the context of propagating wave approximation. And that was our essentially basic motivation for introducing it. The general case, when we do not do any approximations, we still don't have answers to these questions. But when we look at the propagating wave approximation, that means we look at this scattering by this non-local potentials, we have some precise, rigorous results. So to state those results, I need to define a class of potentials for which we could derive these results. We say that a potential which is a bounded potential and it's an integrable function is of class C sub sk. S and k are positive numbers if you have this decay condition at infinities. So v goes to 0 faster than 1 over x to the sigma. And then the function v check k from real numbers to bounded functions of minus 2k and 2k is piecewise continuous. So what is this function? So for each, so you look at the partial Fourier transform of v, which I call v tilde of x. Now for each possible value of x, this is the function of p. This is a bounded function, so this v check hat takes real numbers to bounded functions, and I want that to be a continuous, a piecewise continuous function. For standard potentials which we encounter in physics, this is already satisfied. So this is a quite general case. Now we have this theorem. Suppose your potential is of class C3k. 3 is the decay rate, so it goes faster than 1 over x cubed. Then the following holds. First of all, this operator, this formal expression, defines an unbounded, non-self-adjoint linear operator acting in this Hilbert space. This is the Hilbert space L2 minus k tensor C2. The domain of this operator, the maximal domain, is given by this formula. So you take the range of this omega hat operator. The omega hat was just multiplication by this k squared minus p squared. Now it acts on p's which run from minus k to k, so this is already real. So this is a self-adjoint operator. Its range is dense, and the range of and the domain of D is two component vectors, such that the sum of the two components belong to the range of omega. This is the domain of this operator. Then we could show that the range of this operator is a subset of its domain, which is necessary for the product of these operators to make sense. So these are defined as linear operators acting defined on this domain D. We could write this product of operators as the product of a Hilbert-Schmidt operator and this omega inverse. This is unbounded, self-adjoint, and this L hat operator, which has this simple form, and this e to the 2x omega is a unitary operator. So with this expression, we could look at the problem of convergence of the Dyson series, and we showed that this series converges strongly on this domain. So this makes sense. Furthermore, we could show that its limit of when x minus goes to minus infinity, x plus goes to plus infinity, also exists as a strong limit on this D. So this completes the proof that the transfer matrix for these non-local potentials exists in rigorous term. Next, I'm trying to get to the end of my talk. I want to give you a couple of theorems about the exactness of this approximation. Suppose you have a unit vector in R2, and suppose that you have a short-range potential V such that its two-dimensional Fourier transform vanishes when P dot U hat is less than or equal to 0. That means on this gray half plane. If this happens, we could show that the propagating wave approximation is exact. Next, if we make this condition a little bit more strong, that is, suppose you have a positive number alpha, a unit vector u, such that the two-dimensional Fourier transform of your potential vanishes below this line p dot u hat equals to alpha, that's in this gray region. Now this is stronger than the previous case, so the propagating wave approximation will be exact. But what happens here is that if n is the integer part of 2k over alpha, which means that k, the incident wave, is less than this 1/2 n plus 1 times alpha, then the nth order Born approximation gives the exact solution of the scattering problem. This is the first example, known examples of potentials for which the Born approximation is exact. In particular, if the wave number k is less than alpha over 2, then all the terms in the Born series become 0, and that means that the potential is invisible. If k is less than alpha, then the first Born approximation becomes exact, and as more higher values of k, you always find a finite value of n for which the nth ordered Born approximation becomes exact. Now, this theorem also holds for 3 dimensions. Much of what I said admit 3-dimensional generalizations. So let me give you a concrete example. So what you want, so let me take this, you had to be along the y-axis. Then it's very easy to show that if the Fourier transform vanishes for py less than or equal to alpha, V should have this form for some function W, which has a Fourier transform. If you take W, for example, this form, you get explicit formulas for these potentials. Between a over 2 and minus a over 2 over the x-axis, you have this dependence on y only. Otherwise, it's 0. And this you can use to model an optical system. This is a permittivity profile for a box like this. It's an infinite box, but along y, if y becomes large, it decays quite fast.
Success on these things, not, my judgment of your likelihood of future success.
Excuse me? I could not hear.
No, that was just noise. Please go ahead.
Okay, all right. All right, so this is a particular part. It's a 3-dimensional model, and I'm trying to use 3-dimensional. I mean, it's effectively 2-dimensional, but it works in 3 dimensions, as I mentioned. And you can actually choose these parameters, zeta, alpha, L, to be physically realistic values. So it gives you a complex permittivity profile. That means an object which has regions of gain and loss. And this is the formula to the real part and imaginary part of epsilon minus 1. So there are experimental works on 1-dimensional analogs of this kind of potentials, which were realized. In 2-dimensional case, I haven't seen any experimental work. But in principle, there should not be any theoretical obstacles to realize these in a lab. So this is nice because as I mentioned, for wave numbers less than alpha over 2, this particular setup is completely invisible for all wave numbers less than alpha over 2. It doesn't matter from which direction you have this incident wave coming, it will go through this without any effect. Okay, so let me conclude. I introduced this fundamental transfer matrix in 2 dimensions. I talk about this propagating wave approximation. As I mentioned, our motivation for introducing it was to try to tackle this mathematical problem of existence of this a fundamental transfer matrix M. I showed you that this approximation is equivalent to scattering problems defined by some non-local potentials. I gave you the existence of the transfer matrix for this non-local potentials. And then I switched to address a very, very old problem of the exactness of nth order Born approximation. The Born approximation, as I mentioned, was introduced by Max Born in 1926, the same day, the year he published his famous paper on probabilistic interpretation of quantum mechanics. It's 8 years ago. But still, since our work, there was not even one example of potentials for which this nth order Born approximation was known to be exact. The final word, all our results generalized to 3 dimensions. Also, we have generalization of our approach to scattering, potential scattering to electromagnetic scattering. There is an analog of this fundamental transfer matrix for electromagnetic waves, vector waves, which you can use to handle point interactions, which are much more difficult for electromagnetic waves in a very simple way. Okay, here are the references, and that is all I have to say. Thank you for your attention.
Thank you very much, Professor Mostafazadeh. Thank you for the very interesting talk. Now it's time for questions. So, meanwhile, probably I can ask you one quick question. What can be said about the analyticity of the entries of the transfer matrix in 2D, for example?
So the general transfer matrix, we actually do not know if it exists. So we have examples where we can compute it for like these delta function potentials, but we don't have any control of its general properties. For this non-local potentials, we have a proof that it exists as a linear operator in this Hilbert space that I mentioned, but I can't give you any other information.
Mm-hmm. Okay, thank you. Thank you. More questions, please?
Hello, may I give a question?
Yeah, please go ahead.
My name is Abdon Choke. I have a question about the reference on the factorization of the scattering matrix. As I know, this was proposed by Professor Tuncer Artuson in 1822. 1892.
Mm-hmm.
So is it correct? Because you didn't mention it. So I missed it probably.
Reference to what?
First time when appears the factorization of the scattering matrix.
What appears
for
there?
one-dimensional Schrödinger equation.
Yes. Oh, the transfer matrix.
Yes. So there is also called S matrix, or in other words, the representation of the potential in form sum, as you I think showed. So just as and probably missed it, but as I know, this was first proposed by Professor Tuncer Artuson in 1892.
I couldn't get what I mean. The transfer matrix that in this page that I introduced, this is very old. This is 1940. People knew this, but
I mean the factorization. You mean the factorization?
Even factorization was known in 1940s. So people have used this for numerical solutions of the scattering problem, because you see, once you dissect in 2 pieces, you can dissect to n pieces, and then you develop this numerical way of using transfer matrix for solving problems. So this is not original. What is, it's in 2 dimensions and 3 dimensions. And also the connection to the quantum mechanics. No one could imagine that the transfer matrix happens to be related to some quantum dynamics.
Okay, thank you.
Okay.
Thank you, Abdon. More questions, please? I don't see any hand raised. So probably there are no questions. In fact, I had some questions during your talk, but you were answering my questions.
Well, I couldn't see you because somehow I could only see my own slides.
Yeah, it's okay. It's
So
normal for the Microsoft Teams.
yeah. So I'm accustomed to Zoom, but this is the first time I use this Microsoft Teams.
Okay. So if there are no more questions, then let us thank you again. Thank you for accepting this invitation and for the very interesting talk.
Thank you. Thank you.
Thank you.